Hello and welcome to another video. In this video, we're going to be continuing on with the TypeScript line 75, and we're going to be doing longest increasing subsequence. And this is a really popular interview problem, so I definitely recommend knowing this one. And so here, you're given an integer array nums, and you want to return the length of the longest strictly increasing subsequence. So in this problem, we have like this, and the longest increasing subsequence is 237101 in this one. So in the second example, what's our longest increasing subsequence? Well, it's 0, 1, 2, 3. And in the third one, it's just a 7 because there's only one 7, right? So the most popular way of doing this question is dynamic programming. And basically, I'll briefly talk about it, and then we'll talk about the other way that's more unintuitive. So pretty much the way to do it with dynamic programming is you literally start at, you make an array, and you make every element have length 1, and you go left to right. And then you just check for every number. If there is a number before that number that's smaller, then we can see like how long that is. So we can briefly talk about how we build that for this one. Let's say for this example here. So for 10, it is length 1. For 9, there's nothing to the left that's smaller, so it's length 1. For 2, there's nothing to the left that's smaller, that it's length 1. For 5, there is 2 that is smaller. So we just take whatever the value of 2 was and we add 1, because we can essentially just add the 1 to the end of it, because we can always, if our number is bigger than the number of 4, we can take whatever that value that had and add 1, right? So if 2 had length 3, we can just say like, okay, well, we'll take that length and we'll add the 5 at the end of whatever ends with 2, and then that's an increasing subsequence. So for 5, we would have 2. Then for 3, there is something that's smaller, there's a 2. So for 3, we would have 2. Then for 7, there is something that's smaller. There are a bunch of things that's smaller. And essentially, you take the biggest value of the things that are smaller. So for 7, 2, 5, and 3 are smaller, right? But 2 and 5 have length 2, so we're going to take one of those, add 1, so 7 is going to be length 3. 101, the biggest thing that we can add is going to be the 7, which is length 3. So then we're going to have length 4 here. And for 18, we can add the 7 as well, so that's length 4 as well. So then we will have the biggest increasing subsequence will be length 4, which is 237101 or 23718. That's a DP approach. Now, the other tricky way is we're actually just going to build up our subsequence in a way that will optimize it, and then later on we will take the result. So what we're going to do is we're going to take values, and then every single value we're going to see like, can we replace it? So let me show you kind of what that's going to look like. So for 10, there's going to be nothing there. Then for 9, we're going to say, okay, we have 10, but would we rather have 10 or 9, right? We can only have length 1, but we'd rather have 9, right? Because 9 is easier to build on. So we're actually going to replace 10 with 9. And then we have a 2. And we're going to say, okay, well, we can't have 9 and then 2. But would we rather have 2 or 9? So we'd rather have 2 because 2 is easier to build on. So then we'd have 2 here. Then for the 5, we're going to say, okay, well, can we build on what we have or should we replace it? Well, we can just build on what we have, right? We can just add, like we want to make it as long as possible. Then for 3, can we optimize anything? Well, yeah. So we have a subsequence of length 2, but we want to replace the 5 with a 3, right? Because that would make it more optimal. So we're going to replace the 5 with a 3. And then for 7, do we want to replace something or can we add? And adding is always going to be better because that's going to make our result bigger. So if we can add, we'll add. If not, we can see if we can replace something. So here we can't replace anything, so we'll add the 7. Then for the 101, do we want to replace or add? We want to just add. And for the 18, do we want to replace or add? Well, we can replace this 101. So we'll have 18 here. And let's kind of walk through the second example doing the same exact thing. So we're going to add a 0 because there's nothing here. Now for 0 or 1, so if 1, we can just add to the end of 0. So we're going to want to add. Then we have a 0. So we already have a 0, so we don't really need to do anything. Because we can't have like 0, 0, right? It has to be strictly increasing. Then we have a 3. We can just add to the end. Then we have a 2. So do we want to replace something? Well, yeah, we want to replace a 3 because the 2 is smaller. And then finally 3 you can add. And so the length of your subsequence is 4. The longest one is here is 4. And then for the 7, it is all the same, so it's just going to be 1. And let's say you have something like, this is the reason why you want to replace things. Let's say you have something like this. So the answer here should be 4, and let's see what that's gonna look like with replacing, right? So 4 we're gonna add, 5 we're gonna add, 6 we're gonna add. Now 1, we're gonna try to replace the smallest number we can, because we can't have a 1 here. This still has to stay increasing, right? So we're going to replace the 4 with a 1. Then for the 2, we're going to replace the 5 with a 2 to keep it strictly increasing still. And for the 6, we're going to replace that with a 3. And finally, we can add the 4. So if you do this, we're essentially, we can write this down. So 2 choices. And this is counterintuitive, and I didn't think of this one. So definitely this wouldn't be one that I would, come up with in an interview, but it's kind of good to see. So you're aware of 2 choices. Add on, which we should always take, or replace the, I guess it's going to be like the smallest element bigger than our value, pretty much, right? Yeah. So it's not really going to be, it's not going to be the smallest element bigger than our value. No, I think it's actually correct, I believe, right? So if we have like, let's see, so if we have like 2, 6, 8, and we try to add like 4, yeah, we would want to replace the 4. So it is replace the smallest element bigger than our value, essentially, right? Okay, so that's pretty much what we do, and then at the end we just return the length of our result, and that's pretty much it. And so notice that our array is always sorted, right? When we build this up, we're always sorted. So if we have this like 2, 6, 8, it's always sorted increasing, and we try to add a 4, we can just binary search to find what element to replace. We can just find like, okay, well, what's an element bigger than our value, and is there an element to the left that's bigger? And we want to find the leftmost element that's bigger than our value, and replace that. So essentially, we are cutting it from n squared, which is our dp, to n log n, because every element to put it in is log n time, and you have to go through every element. So now we're going to code up this this solution where we're just building up and then replacing elements. And this does work for everything. You might get some weird solution at the end, but it still works out, essentially. Like this, it won't always represent the exact longest increasing subsequence, but the length will always be correct. So let's code it up now. So we have a result. It's going to be a number array equals just empty array, right? Then we're going to go through every number. We don't really need the index. We just need the number. So for let num of nums. Here. So essentially, for every number, what we need to check is if the result isn't empty, right? Or so I guess, yeah, if the result isn't empty, then we need to be pushing, essentially. Actually, no, sorry. We need to check if the result is empty, because let's say our array is empty, then we can just push the number right away, right? So if not res.length, or if res.length equals 0, or the number is bigger than the biggest number in the array, which is res.length minus 1. So either way, if it's empty or the number is big enough, let's push. And then I'm actually going to have it continue here because I don't want to have like a huge else. So I'll just continue here so we don't get into an else, so otherwise we can have stuff. So the last part is the binary search. So we just have let L equals 0. Right equals res.length minus 1, right? These are our 2 like places we can put in, and essentially we're going to be overriding an element. So the position we're going to be putting it into, we're going to default it to the right, right? So worst case scenario, it's going to be the right, and then we're going to try to get it as left as possible. So we're going to say while left is less than or equal to right. Let's just get a pivot as always, right? So const pivot equals math.floor left plus right on 2. So we get a pivot, and then if the number is less than the result value of the pivot, we'll record that. So if number is less than result at the pivot, we want to record that position because that's going to be a better position, and then we want to go left. Otherwise, if the number is too big, then we'll just go right. And there we go. And then finally, we want to replace that number with whatever position we got. So whatever position we found that was the best one, let's put the number there. And finally, let's return the length of this result because we built up our subsequence in a way to allow for the optimal length. So we can just return here. And yeah, like I said, this one is definitely kind of tricky, and even once you see it, it might not be super intuitive how it works. So, but the DP one definitely should be able to code that up, no problem. And I actually do have like a DP solution to this problem that I'll link. It's a Python one, but it's fine. It's basically the same thing. So as you can see, this one's a lot more efficient. Well, compared to most anyway, because it's n log n compared to n squared. So yeah. And yeah, that's going to do it for this one. So before we end here though, so let's go through the time and the space here. So time, so we are looping through every number, right? And then we have a binary search for every number. So that's going to be n log n. And for the space, we did create this like result array, right? So that's going to be O of n space, which is the same as you would get for a dynamic programming, except dynamic programming, your time would be n squared. But like I said, in an interview, I definitely not do this problem or this solution. But if you have all the time in the world and you want to see other solutions, which are good to know, because I do think the more solutions you know, the more patterns you can recognize. And if you see something like this in the future, then you'll be able to recognize it next time. So that's all. And if you like this video, then please like it and please subscribe to the channel. And thanks for watching.